Hello FIT 2102 students. I'm going to give you a little walkthrough of this exercise 5 of the week 4 tutorial exercises, the pi approximation. So hopefully by now you've already attempted this for yourself, and your solution that you came up with may not be the same as what I'm about to show you, and that's fine. It's fine if you did it in your own way, but if you at least tried to use the observable streams to implement the result. However, the solution I'm going to show you now will be trying deliberately to use only strictly pure functions everywhere except in the subscribes, and it's going to try to use RxJS in a quite idiomatic way, that is in a functional reactive programming way. But everything that I'm about to use is described in the course notes, so if you haven't already, I do encourage you to go and read that now, the section on functional reactive programming. I'm going to use some things here that you may not have thought to do, and I'm going to use some things that perhaps you didn't realize were available to you. And as I said, if your solution is different, that's fine for this week, but hopefully you'll be able to use these ideas in your assignment. In fact, we do expect you to use these ideas where applicable in the assignment to get a really good mark. Here I am in VS Code with the code in front of me, and I am building the code continuously. I have already started an npm run build in this terminal on the right hand side. The code is built, I believe, and if I open it up in a browser like so, then we see that we are planning to, let me zoom this in, then we see that we are planning to compute a pi approximation and put our estimate for pi in this text field here, and we're going to do that by randomly placing dots in this square and a circle inside the square, and we're going to use the ratio of the number of points that fall within the circle versus the total number of data points in order to estimate pi. The number of points that fall within the circle divided by the total number of data points times 4 will be pi. Estimate is based on the simple idea that if we randomly place enough points, then this ratio, the number of points that fall within the circle divided by the total number of data points placed so far, will converge to 1/4 of pi. All right, so let's make this terminal, make our text editor a bit bigger here, like so, and now we can see what we're doing. All right, firstly, looking at what we've already got here, so up the top there's a little class that gives us a random number generator. There's some setup stuff here. There are some data types that I've created for you to use if you like, and a few handy functions down here, including a function to test if a point is inside the circle or not, and a function that's not completed yet, which will, or rather at the moment it's hard-coded to draw precisely one circle, and down the bottom is our first use of observable. So we're generating a stream of counts every 50 milliseconds using this interval function, and that stream is piped into this mapping of the next random function over the input stream. So it's going to be effectively an observable stream of random numbers. We can see that if we subscribe to the stream like so, and if we just pass console.log directly into the subscription, then reload and open up the console window, we should see a stream of random numbers like so. So that's great. And we could go on to solve this problem, extending this pipe by creating another map that perhaps generates another random number using this next random and puts it together in a pair with the first one, and then perhaps in a subscription it would actually draw the dot on the screen and do the little calculation, or it could use mutable variables to count up the number of dots inside and outside the circle and perform the calculation that way. But that would be quite, apart from first use of the pipe, that would be quite an imperative solution. Most of our code would be inside the subscribe. So rather than that, let's try to solve this problem using pure code as much as possible, perform as much of the computation inside observable stream functions and operators, and let's try to use strictly pure functions in all of those observable operators, and keep our subscriptions as minimally complex as possible, just the effects, such as drawing the dots on the screen and outputting the pi approximation. So one problem that perhaps you haven't realized with this is that already here we have some effectful code happening. This next random function is in fact effectful. You may wonder why, because all it's doing is giving us back a random number for every input element, but this random operates over an instance of the RNG, which we create here with a seed for the random number generator, and then next random produces a random number using this next float function, and then it does a little scaling of it to be in the range -1 to 1. Why is that effectful? Well, if we look up at the definition of the random number generator, we see that inside this, so next float calls next int, and inside next int actually mutates one of the properties of this class. This state property changes, this state member changes every time next int is called. So, and basically uses that as the seed for the next float that's going to be generated. This random number generator is simply generating a sequence of numbers. Each one is a mutation of the previous one based on a little mathematical manipulation of the previous one. So this RNG class is stateful, and calling that next random function causes the internal state of this RNG class to be mutated. So perhaps the first thing we'll do is we'll change this RNG class to hold no state and to be strictly immutable. How can we make sure that it's strictly immutable? Well, we can define all of these properties as read-only, like so, and we'll make this one read-only as well, and this one, perhaps we don't even need this state thing here. All this is actually, let's simplify this. We don't need any of that because it's just setting up the seed. Instead, we'll keep that state variable. We'll say we'll have a read-only state member on this RNG class, and now next int is not going to mutate the state. Instead, we will just call it an int, so not next int, but just an int that performs this little computation here. And then float is going to return int, like so. And instead, we'll add a new next function that, rather than changing or mutating any state inside this class, it's going to create a whole new random number generator using the previous int, or the current int, as its new seed. So this next function doesn't mutate anything inside here. Instead, it gives us back a whole new random number generator. So now let's get rid of all this stuff. So the idea of this now is that we can generate a sequence of random numbers by, for example, going R1. Our first one is going to be a new RNG with some arbitrary integer seed. And then our next random number is going to be based on the next function applied to R1, and so on. Right, so there's the beginnings of a random number sequence. The question now, that little bit of state that was previously managed inside, sort of invisibly inside the random number class, has now been externalized into the notion that there's going to be an entirely new random number generator as a result of each one of these next calls. And we can actually get back our float or int random numbers from each of these, like so, and so on. But the question is, how can we generate a stream of these random numbers where we need to maintain a little bit of state from one iteration to the next, which is the previous iterations, the previous element of the sequence's RNG object. How are we going to do that? Well, if you need to maintain or have a memory of what's come before in a sequence, the function in an observable stream, the function to use is scan, as we've seen in the course notes and in some other examples we've seen. And scan is another operator like map and filter, which we can import from the RxJS operators. Now, instead of this map over this next random function that I've deleted, we are going to do a scan. And scan is a function like reduce that takes a function to perform the accumulation from one element of the sequence to the next, and that function takes two arguments, well, three, but we don't care about the index, so two arguments, an accumulator and a value, which is the incoming value in the sequence, and then it returns the next value for the accumulator. And then the second parameter to the scan function is a starting state, an initial state. So perhaps let's just sketch out what this is going to look like to start off with. So our accumulator function is going to have an accumulator, some value coming into it, which actually we don't care about. That's just the numbers coming from this interval function, which we're not going to use at all. We're going to completely replace those with our random numbers, as we did before with the map. And so what are we going to return? So A is actually, well, we'll call it R actually, because it's one of these RNGs. And what we're going to do then is we're going to return a next. And our initial value to the scan sequence is going to be a new RNG with an arbitrary seed, pick any number. Right, so now that type checks, we have a scan that takes a number that we don't use, we don't really care about, and it produces a stream of RNGs. And each RNG is going to be based on the previous one. And from this now, we can generate a sequence of random numbers. So right now, this random number stream is actually a stream of RNGs. Instead, that's not what we want. We want random numbers. We want numbers. So we are going to do a map, and our map function is going to take one of these r's, and it's going to call r.float, like so. And now we have an observable of numbers. And again, if we print them out, we see a stream of numbers in the range 0 to 1. Remember, we're going to need to use this encircle function up here to test if the point is inside this unit circle or not. This encircle function expects a number in the range -1 to 1. That's just how it works. It's going to use this little Euclidean distance test to see if it's inside the unit sphere, the unit circle radius. So we're going to need to generate for this a random array of points in the range x -1 to 1 and y -1 to 1. Let's actually just refactor these types up here a little bit. So actually what would make more sense to use with this encircle function is the notion of a single point, which is a pair of x and y, and then a dot, which is what we're going to draw on the screen, is going to have a center, which is going to be a point, And it can also have a color that doesn't need to be optional like that. Let's make it compulsory. And now, once again, the data that we're going to collect, eventually, leaping ahead a bit, the data that we're going to collect is going to be a pair of counts, the numbers inside the circle and the numbers outside the circle. I might just change that as well while I'm at it. You'll see why in a second. So obviously we can still get total count by just adding these two together, but this data that we're going to eventually build up is going to be a count of the points inside the circle and the points outside the circle. Now this type has changed, so that's a point, and now our in circle is happy again. So now let's generate a sequence of not just random numbers, but random number pairs, random number points. How can we do that? Well, we're going to need two random number streams, aren't we? And how can we take two random number streams and put them into pairs? Let's use another function from RxJS called zip. And zip is not an operator, it's actually a function that works outside of pipes, as we'll see in a second, and therefore it comes from the main RxJS library. And down here, instead, we can take this random number stream, we can take two of these random number streams and zip them together. Oh, actually, one thing we need to do is we need to have streams that have different seeds, otherwise they'll always be identical, and the pairs of numbers, our points, will always be just on the diagonal. So we need to parameterize the seed. Well, I need to turn this into a function and parameterize the seed. So let's do that. Put this seed down there, and now random number stream is a function which takes a number, and so let's seed our first random number stream with 1 and our second random number stream with any other integer. Let's go with 2. And now this zip is producing, as we can see, pairs of numbers. We can print that out. We can simply add this subscribe to the output of zip, and we can open up the console, and we see now pairs of random numbers. Great. And so turning those into points now is fairly trivial. It's just a matter of adding a pipe on here and mapping our pairs of x and y to a point, which we're going to create just like this, x and y. Okay. So we've created an object that is that we have declared is of type point, and so now when we refresh this, we see instead of arrays of two random numbers, we have objects with x and y coordinates. You'll notice that they're not quite in the right range for our in-circle function, which is expecting -1 to 1. So scale the floats, double the floats, and then subtract 1, or vice versa. And now we have numbers in the range -1 to +1, which are ready to go into our in-circle function. So our point stream now, we're going to use it in a couple of different ways. Firstly, to test for points inside the circle, and then to test for points that are outside the circle. And so, because we need to reference it a couple of times to do that, let's name our point stream, following the RxJS convention of putting a $sign at the end of the variable name to indicate that it's a stream. So now we have a stream of points. Let's not subscribe to it there. Instead, let's subscribe to it down here. And now let's differentiate our inside points by taking our point stream and piping it into a filter and how can we filter out everything that's not in the circle? Well, we can just use this inCircle function, which operates over points, so it's ready to be passed directly into filter. And now, what do we want to do with the points inside the circle? Well, ultimately, we want to actually draw them on the screen, don't we? So perhaps let's see how we can get them ready to pass into this create.function. function. At the moment, our create.function function doesn't have any parameters. It is hard-coded to draw a circle at x equals 50, y equals 50, and they're always going to be red. So let's add some parameters up here. And in fact, let's make it a dot that's going to come in. Remember, our dots have a center and a color, so that's exactly what we need. So we don't need this hard coding anymore. And we'll get our x from the d.center, and we'll get our y from the d.center, and our color, which we haven't said yet, can also come from the d.color. Somewhere down here we've got to set that up. So now's the time to turn points into dots. So let's take our points that are inside the circle and map those points into dots, like so. So a dot is going to have a center at point P, and these dots are going to be green because they're inside the circle. Instead of printing them to the console, let's take our inside points and we will create dot them, like so. And what's going to happen? Well, let's have a look. Well, we got one dot, great, very close to the top left. Why? Well, remember our points at the moment are all in the range -1 to +1, subject thanks to that scaling up there, ready to pass into inCircle. What we need now is we need to put them into screen coordinates. And our screen coordinates are the extent of this square, which runs from 0, 0 up here to something like whatever the width and height is. And the width and the height, in fact, I've encoded in well, based on the circle radius. So the circle has radius half of the width and half of the height. So we need to scale these points so that they cover the whole extent of this rectangle. So they need to go from -1 to +1 instead to 0 to the width and height of the rectangle. We can use this handy variable I've defined up here, which, oops, not that one, the circle radius is obviously this half the width or half the height. Let's do another mapping here over the points. Let's apply a function called scale point that we will write now. We'll put it, I guess, up here along with our previous random number string function. So let's scale point be an operation over a point that creates a new point based on some scaling of p.x and also a scaling of p.y. What's the scaling? It's another function that we're about to write. So scaling a value from the range -1 to from -1 to +1. Our new scale has to go from 0 to some extent, so let's get it back to 0 first. So it'll be v plus 1, and then let's multiply that. So this is now going to be a number in the range 0 to 2, and let's multiply that by circle radius, like so. And hopefully now, when I reload, we get points inside the circle. Just making this bigger so we can see this extremely long line of code. Let's now make the outside points. Outside stream is going to be based on our incoming points, our full point stream. We are going to need to filter again. Now this time we're going to want to filter stuff that's not in the circle. How can we do that? Well, we could take a point and we could test if it's in the circle, and we could do some Boolean logic. But can we do that without having to define a function here? What if there was a useful function that could take any function that returns a Boolean result and invert it? Let's call that function not. Seems logical. So what does a not function look like? Not is a function that takes a Boolean function, and that function is intended to be applied to some value, and it's going to apply the function to the value and then invert the result. So now we can filter not in circle. Nice. And the rest of this pipe, I guess, is going to look similar to what we have above. So we're also going to have to scale the points, and we are going to have to map them to dots as before. But you know what? Instead of typing all this code out twice, why don't we refactor some of this out into a function? That's the functional programming thing to do. Let's make a new function. If you've got something you want to do more than once, that can easily be parameterized. Make a function. So what do we call it? How about something like make dots, or points to dots? Points to dots? Make dots? Make dots. Equals all that stuff we just copied. And we're going to parameterize it with the filter predicate. And also the color is the only other thing that really needs to be parameterized, because our dots inside the circle are going to be green and our dots outside the circle are going to be red. So there's our color, and here's our predicate, and of course, and we're piping over the stream of points. Actually, I should have taken that with me, because we can hard code that as well. Because we now down here, instead of all this stuff, we just go make dots, and our test is in circle, and our color is green, and then this one is going to be make dots not in circle, and those ones are going to be red. So now we can subscribe to our outside points and see what we get. Right, so we get green dots inside the circle and red dots outside the circle. Fantastic. What comes next? Well, now we need to use all these points inside the circle and outside the circle to actually perform to calculate our pi approximation. Our pi approximations are going to be a sequence of gradually improving approximations based on the running counts as they come in. And so to do that, we are going to need to somehow bring these two streams back together in order to get the number of points inside the circle and the number of outside the circle. How can we bring points, how can we bring two streams together? Well, there's a handy function in RxJS called merge, sensibly enough. So we would simply merge our inside stream and our outside stream of points. And so now, what's merge return? It returns dots, an observable of dots. So now we have a single stream of dots. Some of them will be inside, some of them will be outside. How can we differentiate? Well, some will be green and some will be red. Now, to keep track of counts, again, we need to have a little bit of memory of what's come before in the sequence. How do we do that in RxJS? Well, it's similar to how we remembered the random number generator from one element of our random number stream to the next. We used a scan. This is a stream of dots. Let's call it that, so it's easy to remember what we're looking at. And now we can scan over the dots. Let's put that into another stream, which we will call PiApproximations. And our pipe is going to scan. What are we doing now? Well, we're scanning again. We need an accumulator function. What are we accumulating? Well, this time let's use our data structure that we defined before. So our accumulator is going to be a data element with an inside count and an outside count. And the values coming in are going to be dots. Let's call it D. And our function is going to test if the color of the dot is green. Then we are going to increment the inside count. Oops, inside count. And we are going to keep the outside count the same, like so. And the alternative branch is going to be inside count is the same, so the other thing above flipped, and the outside count is going to be outside count plus 1. Okay. I think scan is complaining because it hasn't figured out what these types are yet, and we haven't, and part of the reason is because we haven't given an initial value for the scan. So the initial value is going to be another one of these objects that is going to have an inside count of 0 and an outside count of 0. And now it's happy about the types. It hasn't actually realized what's it saying. Yeah, so it hasn't actually realized that this object with an inside count and an outside count is a data. Let's tell it that it is. So the type of scan is it takes a dot coming in and it gives us back a data, like so. And now it's happy that it's a scan over dots producing a data. Alrighty, so there's our scan. And what are we going to have then? We're going to have a stream of these counts. How can we turn those into pi approximations? Well, now is the time for a map. So we are going to do a map over an inside, oops, brackets everywhere, an inside count and an outside count. And we are going to perform our calculation. So what did we say before? We need our inside count divided by the inside count plus the outside count, so the total number of points, and we're going to multiply it by 4 as per the instructions up here. Right. So, is that going to work? Let's put it into, up here is the instructions for how to set this this text here. So result in page. Let's create a new subscription over the dots, and so these are, oh no, sorry, over our pies. And these we want to, let's call it pi, and we'll do that thing of taking the result in the page. It's a number at the moment. Let's make sure it's a string, which is what the inner text is meant to be. And now, when we reload our page, yay, we get numbers that look like very bad approximations of pi. Gradually, ever so gradually getting better. Okay, so I never said this is a good way of approximating pi. In fact, it's a pretty terrible one. But the point is that we have put the algorithm for calculating this into this functional reactive programming style. And what that has done for us is given us a fairly straightforward way of plumbing these various streams, transforming these streams of one type of object into a stream of another type of object, and then plumbing them together, either splitting them apart using our filters up here. So that created two different branches over our original input point stream, which, remember, was already a convergence of two random number streams zipped together. And then we have two separate streams, some of them points inside the circle, some outside the circle. Then we merged them back together. So now we have a common stream of dots, some of them green, some of them red. And then down here we take those dots and turn them into pi approximations by scanning to perform the count, keep the count of the inside points and outside points, and then finally mapping it over those inside-outside counts to do the little calculation to turn them into actual pi approximations. Speaking of which, there's a bit of excess code here now because we don't need to draw those things separately. We can just draw them. Oops, no, it's a dot stream that we're drawing. We can just draw our dots like that. So now the outputs, the effects of all this computation are just in these last two lines. So we're drawing dots and we're updating the pi approximation text on the screen. So these are the only effectful computations in all of this code. Everything else is completely pure. Right down to our random number generator, which we saw at the start. And so I encourage you to work through this code and get clear in your own mind, confirm in your own mind that all of these functions are pure and that these are the only place we have our effects. And after a while, it will be easy for you to conceptualize these manipulations over streams as like a wiring diagram, or, like I said, a plumbing diagram in your head of how things split apart and join back together. They're literally flows of objects being transformed, split, merged, and so forth. So I hope that makes sense to you. This is the kind of idiomatic functional reactive programming style that we would like you to use in your first assignment. So good luck with that. I hope you get your head around it and enjoy it. It's really satisfying once you get used to programming in this way, and leads to quite robust code. This separating out of the pure computations into streams, and the effectful code limited to just a single place is very satisfying and tends to be very robust. All right, so that's it for now. Good luck with the assignment 1, and I'll see you in class.